Hello everybody. Today I will be covering section 4.3, which is about sine, cosine, and tangent functions. And specifically we're going to talk about their graphs and also how to perform transformations of sine, cosine, and tangent functions. So as I've mentioned in either class or in Zoom videos or in our Zoom meetings, that it might be a good idea to go back to section 1.5 of the textbook and review transformations of algebraic functions. Now, of course, these transformations will be defined in the same way, except for we are going to be able to exploit some of the repetitive nature of the graphs of sine, cosine, and tangent to produce graphs of transformations of sine, cosine, and tangent. And it all relates to something called, or much of it relates to what is called the period of the sine, cosine, and tangent functions. So just a reminder, at the very beginning of section 4.3 in the textbook, we have the graphs of sine, cosine, and tangent. Now, one thing I want you to notice is that for sine, if you start at minus 2 pi and you go 2 pi units to the right, that'll bring you to the origin. And then the graph from 0 to 2 pi is just another copy. So one thing you notice is that on every interval of length 2 pi, the graphs of sine and cosine will repeat themselves. Whereas on the graph of tangent, you can see that the graph is just a bunch of copies of what the graph looks like from minus pi over 2 to pi over 2. So this graph repeats itself. You'll notice that every repetition happens over an interval of length pi. Okay, so that brings us to the notion of periodic functions. So in the very beginning of the textbook, this is in the interactive ebook, they give you 3 examples of what a periodic function looks like. So here's an example of a periodic function. You can see that the graph is basically just a bunch of copies of itself that repeats over every interval of a certain width. The same thing would be true here. And so what I'm saying is for the first one, right, so here's just maybe one piece of the graph, and you'll notice that all the rest of the graph is just copies of that piece. Or in the second periodic function, again, you have a graph that copies or repeats itself over every interval. So you'll notice that this one piece of the graph, which is those 3 horizontal line segments, just repeats itself over and over again. The same would be true of the third function here. This would actually be the graph of sine right here. And again, here's maybe just the part of the graph that's repeating itself. If you look at the interval from 0 to 2 pi, you get another copy of that piece here to the left from negative 2 pi to 0. And the rest of the graph would just be copies of these pieces over every interval of length 2 pi. Now, and then there's one more graph here of one that is not periodic, because here's a graph that doesn't really repeat any part of the graph again. So you'll notice that none of these little pieces are being repeated. None of these little horizontal line segments happen again anywhere else on the graph. So this is an example of a graph that is not periodic. Okay. So let's take a look now at the definition. So again, sine, cosine, and tangent are what are called periodic functions. And a function f is said to be periodic if there exists a non-zero real number p such that f of x plus p has the same value as just f of x. Okay, so by adding p to the input, the value of the function does not change. And we saw this with sine and cosine in the previous section. We saw that for any angles that are coterminal, which are just basically taking your given or original angle and adding or subtracting any multiple of 2 pi, you would get the same function value. Now, the period of f in the next sentence is the smallest positive value p, so that f of x plus p equals f of x. And one cycle of a periodic function occurs for every period. So basically a cycle is the part of the graph that is being repeated over and over again. And whatever the period is, that would be the width of the interval corresponding to that cycle. So, for instance, for example 1, see the ebook. For each of the functions in the interactive figure that are periodic, find the period p. Okay, so here are those 3 functions. So I'll do the first one here. Okay, so here's a function that is periodic, and I will highlight one cycle. So if you look at the first piece, from 0 to 2 on the x-axis, this would be one cycle. And the width of the interval corresponding to that cycle would be the period. So if you look at that piece that I've just highlighted, the range of x values on that piece would be 0 to 2. So the width of that interval would be the period. And I'll use capital P for the period. The period of this graph would be 2 because every cycle occurs on an interval of width 2. Okay, you'll see here's another cycle. Okay, going from x equals 6 to x equals 8. And again, that cycle also has width 2. And sorry, I might have already said this, but the video seemed to pause on me while I was recording. So what I have there is, in the picture, this is for the second periodic function. I have boxed 2 cycles, so those are 2 pieces of the graph that are identical to each other than they've been shifted left or right. And if you look at one of the cycles, the width of the interval corresponding to that cycle would be 4 units. So that one cycle that I've highlighted there goes from x equals 0 to x equals 4, or on the left you go from -8 to -4. In either case, the width of the interval corresponding to that cycle is 4. So the second function is periodic with period 4. And the third function that is periodic, I'll highlight one cycle again. So if you look starting at x equals 0 and you go to x equals 2 pi, there would be one cycle. And you can see that piece of the graph is also repeated to the left from -2 pi to 0. And again, a periodic function just repeats itself. You're just drawing copies of those cycles. And if you look at that first cycle that I boxed, that piece of the graph extends from x equals 0 to x equals 2 pi. So in this case, this would be a periodic function with period 2 pi. And of course, this is the graph of y equals sine of x. Okay. So again, if you want to find the period from a graph, you locate a cycle, and the width of the interval on the x-axis corresponding to that cycle is the period. Okay, so now we can talk about the periodic properties of sine, cosine, and tangent. Now again, if I go back into the textbook here, and I go to the first figure, this would be figure 4.18. If you look at the graph of sine and cosine, just looking at the graph of sine, again, here's one of the cycles, and it corresponds to, or that cycle has a width of 2 pi, so that would be a 2 pi periodic function. And here's cosine, and again, you can probably convince yourself that this is periodic with period 2 pi. So again, there's one cycle, and in the graph of cosine is just going to be a bunch of copies of that cycle. And then finally, you have tangent theta, and I'll draw again. Here's one of the cycles. So that's one part of the graph that repeats itself over and over again, and it's the smallest such possible cycle, so you can't make anything smaller. And the width of the interval corresponding to that cycle going from -pi/2 to pi/2 would be pi. So sine and cosine are 2 pi periodic, and tangent is pi periodic. So to summarize, the functions sine, cosine, and tangent are periodic with periods 2 pi for sine and cosine, and period pi for tangent. Okay, now in the examples here, we're gonna use what we know about the periodicity, is what you would say, about the graphs of sine and tangent. In part A, I want to find all of the angles from minus 4 pi to positive 4 pi, satisfying sine of theta equals 1/2. Okay, so for this, I might want to draw a unit circle. Now, if you can find all of the angles from 0 to 2 pi, so that sine of theta is 1/2, you can get the rest by using the periodicity. So you can add and subtract 2 pi as many times as you need. Now, the first thing I want to notice is, and I probably should use a different color, but that's okay. So here's an initial side of an angle. Here's the angle pi over 6. And we know the coordinates of that point right there. We know cosine of pi over 6 is root 3 over 2. We know sine of pi over 6 would be 1/2. And again, this is on the unit circle with radius 1. There is another angle between 0 and 2 pi that has a y-coordinate of 1/2. If you like, you can think about it by reflecting over the y-axis. The coordinates of this point are minus root 3 over 2 comma 1/2. Now, what angle is that? Now, on exercise 44 in section 4.2, we would have seen that in this purple angle right here. This angle right here would be, this angle here is 5 pi over 6. Okay. So in the first quadrant from 0 to 2 pi, you have two angles that give you a value of sine of equaling 1/2. Now, how do I get the rest of them? We're just going to keep adding 2 pi and subtracting 2 pi from each of those angles. So here's what I'm going to do. I'm going to label. So basically, we're finding all of the angles coterminal with pi over 6 by adding and subtracting 2 pi as many times as we need to stay within minus 4 pi and 4 pi. And we're going to do the same thing with pi over 6. So I'll start right here. I got pi over 6. And I'm just going to use the periodicity of sine to keep adding and subtracting 2 pi's to get the other angles so that sine of theta is also equal to 1/2. So you can add 2 pi once. Pi over 6 plus 2 pi, or 12 pi over 6, would be 13 pi over 6. Okay, you can add 2 pi again. That's another 12 pi over 6 to get 25 pi over 6. And as long as 25/6 is less than 4 pi, this is good. But it turns out that 25 pi over 6 is actually too big. Okay, that's actually greater than 4 pi. Okay, so I actually don't want to include that in my list. So starting at pi over 6, I'll subtract 2 pi, or 12 pi over 6, to get minus 11 pi over 6. And I'll subtract 2 pi one more time, so subtract another 12 pi over 6 to get minus 23 pi over 6. And it turns out that if you subtract 2 pi one more time, you're going to be less than negative 4 pi. Okay, so those are the four angles between negative 4 pi and 4 pi that are coterminal with pi over 6. So all those angles would give you a sine value of 1/2. Now you have to do the same thing for 5 pi over 6. Okay, so we're going to start adding and subtracting 2 pi's. 2 pi is 12 pi over 6, so if we add 12 pi over 6 to 5 pi over 6, you get 17 pi over 6. And if you add 2 pi one more time, that'd be adding another 12 pi over 6. You would get 29 pi over 6, but that's bigger than 4 pi, so that's no good. So we don't want that one in our list. So starting at 5 pi over 6, I'll subtract another 2 pi. So 5 pi over 6 minus 12 pi over 6 would be minus 7 pi over 6. Okay, we'll subtract another 2 pi or 12 pi over 6 to get minus 19 pi over 6. And if you subtract 2 pi one more time, you would get negative 31 pi over 6, which is actually less than negative 4 pi. So these are the 8 angles between negative 4 pi and 4 pi that would give you a sine value of 1/2. Okay, part B. Let's find all the values between minus 2 pi and 2 pi satisfying tangent of theta is equal to square root of 3. Now, if I draw the unit circle, and I have to think for a second, I believe this time you're going to find all the angles between 0 and pi, so that tangent of theta is square root of 3. Now on the unit circle, here's an angle in standard position with its initial side on the positive x-axis. And it turns out that the angle of pi over 3 is the only angle so that the terminal side of the angle has slope root 3. So one thing we know for sure from the previous section is that tangent of pi over 3 is root 3. Now tangent is pi periodic. Basically you're looking for angles whose terminal side has the same slope as the terminal side of pi over 3. So I'm just going to extend the line going through the terminal side. And one thing you'll notice is you could take pi over 3 and add pi to get another angle whose terminal side has a slope of square root of 3. So it's not as difficult as the first problem. You would start with, okay, one angle that satisfies tangent theta is root 3 is pi over 3. And then now you can just keep adding and subtracting pi. That's the period of tangent to get all the other angles whose value for tangent is square root of 3. So pi over 3 plus pi. Pi is 3 pi over 3, so you would get 4 pi thirds. You can add pi again to get 7 pi thirds, except for 7 pi over 3 is actually larger than 2 pi. Okay, so the largest angle in negative 2 pi to 2 pi that gives you root 3 is 4 pi over 3. Now you can start subtracting pi from pi over 3. Pi over 3 minus pi, or pi over 3 minus 3 pi over 3 would be minus 2 pi over 3. And I believe you can subtract one more time. If you subtract pi from negative 2 pi over 3, you'll get minus 5 pi over 3. But if you subtract pi one more time, you'd actually be less than negative 2 pi. So there's your 4 angles between minus 2 pi and 2 pi, so that tangent of theta is root 3. Okay, so now we understand how sine, cosine, and tangent are periodic, and we know their periods. And we're going to use the fact that those functions are periodic to simplify graphing transformations. So before I even get started on this, I want to point out that if a function has been transformed, there's always a factor here, capital A, in the expression right here. So starting with let me just read this off. For real numbers A, B, C, and D, with A and C non-zero, and starting with a periodic function f, the graph of y equals c times f of A times the quantity theta minus B plus, outside of the parentheses, capital D, is obtained from the graph of y equals f of theta by performing the following transformations. Now, the nice thing about this is you can actually just think about transforming one cycle. So usually we're transforming sine, cosine, or tangent. And you would take what's called the fundamental cycle, and I'll talk about that in just a minute. But you would just have to think about transforming a single cycle to know what that cycle is transformed into, and then you can draw the rest of the graph by repeating that cycle over and over. Now, the nice thing here is that if you start with say, sine or cosine with period 2 pi, capital A, again, make sure you review transformations in section 1.5. Capital A tells you to do either a horizontal stretch or a horizontal compression. So you'd be taking that cycle of period 2 pi, and you're either extending the length of that cycle or you are compressing the length of that cycle. Capital B is telling you how many units you should shift to the left or to the right. So if your original cycle started at 0, capital B is just telling you to shift that cycle right or left. So it's going to tell you where you would start the cycle in the transformed function. Capital C is a vertical stretch or a compression. So basically on the graph of sine and cosine, you know the highest point is 1 and the lowest point is -1. So capital C is either going to stretch, I guess, it's going to stretch you away from the middle value of 0. And then finally, capital D is just doing a vertical shifting. Okay, so now let's talk about how these factors relate to phase shifts. The horizontal scaling gives you a different period. We'll talk about the vertical scaling, and we'll talk about the vertical shift. Okay, so... All right, so number 1, there's going to be what's called a phase shift. So you're going to take your cycle, or what's called your fundamental cycle, which I guess I should probably show you here just before we get started. So let me open up the textbook. Here we go. So make sure to look at this page about what are called fundamental cycles. So on the top left, you have what's called a fundamental cycle for sine theta. So that's the graph of sine from 0 to 2 pi. The fundamental cycle for cosine is also from 0 to 2 pi. And the fundamental cycle for tangent of theta would be from 0 to pi. So you're always thinking about transforming these fundamental cycles. Once you've done that, then you can just kind of draw the rest of the graph by drawing copies of those cycles. Okay. Make sure you read through that section and you know your fundamental cycles for these 3 functions. Okay, so back to the handout. Okay, so now, again, making sure you look at the general form of a transformation of f of theta. You have an A, B, C, and D. Theta is the input variable. F is the name of the function. So to transform f into the graph of c times f of a times theta minus b plus d, you're going to perform the following transformations. And you're always thinking about transforming the fundamental cycle. So you're going to do a phase shift of absolute value of b units right if b is positive, and you're going to do absolute value of b units left if b is negative. Okay, so basically this just tells you where you're going to start your cycle in your transform graph. So the fundamental cycles all start at 0. The phase shift is going to tell you where your cycle is going to start on the new graph. Okay, capital A tells you what kind of horizontal scaling you're going to do. You're going to do a horizontal scaling by a factor of 1 over absolute value of A. Of course, if A is negative, you also do a horizontal reflection. So there's a horizontal scaling by a factor of 1 over A, and it's going to be, let's say it this way, it's going to be a compression if the absolute value of A is bigger than 1, and it's going to be a stretch So you're going to have a horizontal stretch if the absolute value of A is between 0 and 1. Okay. And the period, okay, so the period of your resulting transformed function is you're basically just going to be taking the original period and multiplying it by 1 over absolute value of A. So the period is 2 pi over the absolute value of A for sine and cosine. And the period of the transform function is going to be pi over the absolute value of A. And you know what? Let's write P equals on both of these for P for period. P equals pi over the absolute value of A for tangent. Okay. Next is you're going to do a vertical scaling by a factor of the absolute value of C. And again, it's going to be this case, it's going to be a stretch if the absolute value of C is greater than 1. And it's going to be a compression if the absolute value of C is between 0 and 1. Again, make sure to review your transformations in our textbook that was covered in section 1.5. Now, let's talk about the amplitude. The amplitude, this is half the difference between the maximum and minimum function values, is always going to be given by the absolute value of C. Okay, so let me maybe show you what I mean by that. Essentially, and again, it's half the difference between the maximum and minimum function values, or you can think of it this way, it's the difference between the middle value in the max or the min. So going back to the textbook, if you're looking at sine and cosine, there really is no amplitude for tangent because there is no maximum or minimum value because of the vertical asymptotes. But if you look at the graph of sine and cosine, sine and cosine have a middle value of 0, and the distance from either 0 to the maximum or 0 to the minimum value would be positive 1. Okay, or it's half the difference between the maximum and minimum. So, right, sine and cosine have maximum 1 and minimum negative 1. So half the distance between those values, which is 2, if you have that, you would get positive 1. So sine and cosine originally have an amplitude of positive 1. And if you have a transformation, the absolute value of capital C is just going to tell you the distance from the middle value to the maximum value on the resulting transformed function. And we'll see how that works in just a moment. Now, there's always going to be a vertical shift. And again, the vertical shift just tells you where the middle value is going to be on your transformed function. So if you look at sine or cosine, the middle value or the function value that's in the middle of the maximum and minimum would be 0. The vertical shift is just telling you where the middle value is on the transformed function. So there's a vertical shift of absolute value of d units up if d is positive, and absolute value of d units down if d is less than 0. Okay. And just a note, I talk about this quite a bit. There's something called the midline. The midline of sine and cosine is y equals 0, because again, 0 is the value halfway between the maximum and minimum. So the midline of the transformed function, and this is the middle value, the midline of y equals cf of a times theta minus b plus d is the horizontal line y equals capital D. And then, like I said, once the fundamental cycle has been transformed, the graph of the resulting function can be completed by making copies of the fundamental cycle. So let's see a couple examples and see how this works. Okay, so here's a couple examples where we have horizontal transformations. So the horizontal scaling is going to alter the period, and the shift is going to give us the phase shift, and that's just going to tell us where the fundamental or the cycle of the resulting graph is going to begin. Okay, so for the first one, g of theta is sine of 2 theta minus pi. Now the first thing you're going to want to do is, here's the general form again of a transformation of g. So it'd be, or the transformation of any function. In particular, here's what a transformation of sine would look like. It'd be y equals c times sine of a times theta minus b plus d. So we must put g of theta in this form first. So g of theta is probably better written by factoring a 2 out of the inside of the parentheses. So since it's 2 theta minus pi, factoring out the 2 on the inside is going to give us sine of 2 times theta minus pi over 2. Right? If I distribute the 2 back through, right, I should get what I started with up top, right? 2 times theta is 2 theta, and 2 times negative pi over 2 would give me minus pi. So I'll identify A and B here. A is going to be positive 2. Capital B is going to be positive pi over 2. Okay, so the period of G is going to be obtained by taking the period of sine of theta and dividing by A. So the period of the resulting graph is now pi. And the phase shift, since B is positive pi over 2, the phase shift is going to be pi over 2 units to the right. Okay. So basically, our cycle that we're going to draw for the graph of G is it's going to start at pi over 2. There hasn't been any reflections or anything. So it's the resulting graph is going to have the same shape as sine of theta, except for the cycle is going to start at pi over 2, and it's going to, that cycle is going to have a width of the period, which is pi. Okay, so that's the first part of the question, is identifying the period and the phase shift. Now let's sketch a graph. Now it's handy to have the fundamental cycle. So what does the fundamental cycle of sine look like? So here's y equals sine theta. Maximum is 1. Minimum is negative 1. Now there hasn't been any vertical transformations, right? So you're still going to have the same midline of 0, and the maximum and minimum of our transform function is still going to be positive 1. But I'll just again draw the fundamental cycle, which is the graph of sine from 0 to pi over 2. Okay, so essentially our graph is going to look identical to this, except for it's been compressed. So instead of a cycle of length 2 pi, the period is pi, so our cycle is going to be pi units wide. And the phase shift is pi over 2 units to the right. Okay, so I'm going to draw the fundamental cycle. So I'm going to draw what the transformation of the fundamental cycle looks like, and then to draw the rest of the graph, we just draw copies of that fundamental cycle. Okay, so it's been shifted pi over 2 units to the right. Now let's just do this to start. I'm going to draw, okay, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. Now, Actually, oftentimes one thing that I do is to help me graph something like this is, since my period is, look at the fundamental cycle for sine. Notice that it's an interval from 0 to 2 pi. And to get all the tick marks, I've divided the period by a fourth, or I've divided the period by 4, right? So 2 pi divided by 4 would be pi over 2. So I'm doing tick marks every pi over 2 units. So this time, since the transform function has period pi, if you divide that by fourths, your tick marks should all be pi over 4 units wide. So I'm going to add some tick marks into our graph. All right, so here's pi over 4 pi, here's 3 pi over 4, and my fundamental cycle then is going to be graphed between pi over 2 and 3 pi over 2. Okay, and it's basically just going to be a copy of the fundamental cycle of sine, except you're going to alternate between 0, 1, 0, and -1 every pi over 4 units. So basically, here's what's going to happen. I got to label my vertical axes with +1 and -1 here. Okay, here's I have a y-axis and I have a theta axis. And so now, again, the phase shift was pi over 2. And you're just going to draw a copy of sine theta, essentially. So instead of, sine has a value of 0 at 0, and since the phase shift is pi over 2 to the right, the transform function has a value of 0 at pi over 2. And then just like the fundamental cycle of sine, a quarter of the way through the period, you're at +1. A quarter of the way through the period of the transform graph will now be at +1. So that's why I drew in those extra tick marks. So that would be 3 pi over 4 in here. I don't know if everyone can see that or not. Pi, and then you have 5 pi over 4 is that next tick mark. So now, in this case, going another tick mark to the right is like going half of the way through my cycle. In the fundamental cycle of sine, going halfway through the cycle, you're at a value of 0. 3/4 of the way through your cycle, you're at a value of -1. And then all the way through your cycle at 3 pi over 2, you'd be back to 0. So here is what if you transform the fundamental cycle of sine for this given function, there's what one cycle would look like. And then now you would just be adding in more tick marks if I want to draw a second cycle. So going to the right, 3 pi over 2 plus pi is actually going to get me over here to 5 pi over 2. And I'll split this interval here, which has width pi, I'm going to split that up into fourths. So if I'm going to complete one cycle through an interval of pi, I'm going to split that interval up into fourths. So I'm going to add 2 extra tick marks. Again, this is an interval of length pi right here. And now I'm just going to repeat the graph. So this would be at 7 pi over 4, you're at +1. At another quarter way through the period, you're at 0. Another quarter way through the period, you're at -1. And another quarter of the period, you're at 5 pi over 2. So here would be another cycle of g of theta. So this right here is the graph of g of theta. And then let's go to the left. So I'm just going to go from pi over 2 to minus pi over 2. That would give me another cycle. And I'll split that interval up into fourths again. And then at negative pi over 2, you're at 0. At minus pi over 4, you're at 1. At 0, you're at 0. And at pi over 4, you're at -1. Here's another cycle. So to draw the tick marks, right, your phase shift tells you where your cycle starts. That was pi over 2 here. The cycle is completed over an interval of length pi. So starting at pi over 2 and going pi units to the right to 3 pi over 2, you're You're going to split that interval up into fourths, and then on that that interval, you're going to draw a copy of the fundamental cycle. Okay, so there would be a graph of g of theta using the period and the phase shift. I actually think this is much easier than transformations in pre-calc 1, where you actually had to pick points off the graph and transform those points. In this case, we get to exploit the fundamental cycle of our periodic functions and really just draw one cycle of the function and then kind of just draw copies of that cycle to get the rest of the graph. Okay, so I just gave you 3 cycles of g of theta, and I could do more if I wanted to. All right, so now let's draw a graph of, or do part B here. Okay, so let's let h of theta be tangent of pi over 3 times theta plus 2. And we're going to find the period and the phase shift and then sketch a graph by basically drawing essentially a copy of the fundamental cycle of tangent. All right, here we go. All right, so again, let's just kind of compare this to a standard transformation. So here's the general form of a transformation of tangent. It'd be c times tangent of a times theta minus b plus capital D. And actually, sorry, but I'm going to write that a little bit smaller. There we go. And for our given function, c would be 1, capital D would be 0. That's why those have vanished. So the value of a here, just comparing it to what we've been given and comparing to the general form, a would be pi over 3. Capital B is actually going to be, so notice that ours is theta plus 2, and the general form is theta minus b. The only way to subtract b and end up with a positive 2 is if b is a negative 2. So we can find the period. So the period of the function that we're trying to graph, since it's a transformation of tangent, you start with the period of tangent and divide by a, which is pi over 3. This becomes pi times, now dividing by a fraction is the same as multiplying by the reciprocal, and pi times 3 over pi is positive 3. Okay, so our function has a period of positive 3. In the phase shift, since capital B is negative 2, the phase shift is negative 2 units, 2 units to the left. I don't need the negative. So that means since our fundamental cycle for tangent starts at 0, when we draw a cycle of the transformed function, our cycle is going to start at negative 2 and have a width of 3 units. So let's take a look again at the fundamental cycle for tangent in the top right. We have the fundamental cycle of tangent theta. And again, we're going to start at our fundamental cycle for tangent starts at 0. Now, tangent is pi periodic. Halfway through that cycle, tangent has a vertical asymptote. And from 0 to pi over 2, tangent increases up and to the right and approaches the vertical asymptote. And from pi over 2 to pi, starting at pi, tangent of pi is 0, and then moving to the left, the graph goes down, approaching the vertical asymptote. So our cycle for our transform function is going to look identical, essentially. It's just going to start at a different value. The new cycle is actually going to be 3 units wide, and halfway through that cycle, there's going to be a vertical asymptote. So let's see what that looks like. I'm just going to kind of box off this right-hand side. So let's see, I need to start at negative 2. That's where we're going to start this cycle. So here's a y-axis. Here's a theta axis. And I'm just going to do, I don't know, tick marks that are 1 unit. So I'm going to go 1, 2 units to the left. And then I'll go 1, 2, 3, 4, 5, 6, and see that where that gets us. Okay. I'm not actually going to label the y-axis because tangent goes up forever and down forever toward near its vertical asymptote, so I'm not going to really bother with that. Now, to show all of you, the phase shift was -2, so that's where our cycle is going to begin. And tangent, this function's cycle or period, it would be 3 units wide. Okay, so as you can see, our cycle is going to start at -2, and we're going to go through one cycle from -2 to +1. Now, halfway through that cycle, there is going to be a vertical asymptote. Halfway between -2 and +1 is -0.5. So we have a vertical asymptote here at -0.5. Okay. And then now we're going to start at -2, end our cycle at +1 to the left of the vertical asymptote. Right now, since the fundamental cycle of tangent is 0 at 0, our transformed graph, or the graph of h, is going to be 0 at -2 and increase towards the vertical asymptote at -0.5. And then the cycle ends at +1, so we're going to be h of 1 is going to be 0, and we're going to go down and to the left, approaching our vertical asymptote. So there's one cycle. There's one cycle of the graph of h. So this is going to be h of theta. And I can draw another one now. So again, now on another interval of length 3, starting at +1, here's another cycle. 2.5 is halfway between there. I'm going to draw a vertical asymptote. And from 1 to that vertical asymptote, we're going to increase towards the asymptote from 1 to 2.5. The cycle ends at 4, and I'm going to go down and to the left of approaching our vertical asymptote. So there's another cycle. And I guess if I just add one more tick mark, I can draw one more cycle for everybody. So let's go from 4 to 7. There's an interval of length 3. 5.5 is where the vertical asymptote should be. That's halfway through a cycle. And to the left of that vertical asymptote, from 4 up until 5.5, the graph is going to increase towards that vertical asymptote. And the cycle ends at 7. The function has a value of 0. And we just go down and to the left, approaching that vertical asymptote. So there is a graph of h of theta. I've really just graphed it from -2 to 7. But again, I drew 3 cycles for all of you. Okay, so there was the first 3 examples. Now I have examples 4, 5, 6, 7, 8. This video is going to have to be split up into 2 parts. So make sure you watch part 2 of the video, but this is going to conclude part 1. Thanks for tuning in, everybody, and I hope to see all of you soon. Thank you.